Hi, I'm Florence Aellen from the University of Bern in Switzerland, and welcome to this oral presentation of my poster called Convolutional Neural Networks Predict Outcome from Coma based on auditory ERPs. Cardiac arrest is one of the leading causes of coma and admissions of patients to the intensive care units of hospitals. It is also the cause of around 17 million deaths every year worldwide. Early medical intervention has a high impact on patients' chance of survival, and for clinicians, it is very important to make an early prediction of outcome for informing relatives and making an informed decision for stopping life support. Once patients are admitted to the ICU, they immediately undergo a controlled temperature management at either 33 or 36 degrees Celsius. In the following, I will call temperature management at 33 degrees hypothermia and at 36 degrees normothermia. During their stay in the hospital, clinicians perform numerous evaluations on the patients, one of them being EEG recordings, until either the patients recover, they die, or life support is stopped. For the latter, clinicians base their decisions on a multitude of markers, most of which are based on visual evaluations, such as the example here, where we have an EEG recording and a clap performed next to the patient. You can see a decrease in the amplitude of the EEG after the clap, indicating a reactive EEG background, which is a marker for good outcome. For our study, we selected 4 currently used markers. If they did not agree on the patient's outcome, and clinicians therefore would not be able to make a precise prediction, consider these patients to be in an uncertain state, a so-called gray zone. For our data set, we found 1/3 of patients belonged to this gray zone. Currently, clinicians have a lot of markers indicating bad outcome, and only a handful for good outcome. Most markers for a good outcome are related to auditory stimulations. This example shows on the right side a patient with an N100 response, whereas the patient on the left side did not have any response. The presence of an N100 can be an indication of a good outcome. However, these studies were only performed at later stages of coma and on single electrodes. More recent attempts used multivariate decoding algorithms. They trained per patient a machine learning algorithm on the EEG data and have found a predictor for good outcome. In recent years, computer vision, and especially deep learning, have gained quite a lot of attention, as these powerful algorithms are used for predicting images, videos, and a multitude of other things. They have been used for decoding EEG already, and more specifically, they have been used for predicting outcome of coma based on resting state EEG. Here, however, we hypothesize that convolutional neural networks would be able to extract patterns of EEG responses to standardized auditory stimulations, and that the networks could improve outcome prediction for patients in an uncertain state. We are using data of 134 patients on the first day of coma after cardiac arrest, exposed to auditory stimulations. We have 79 survivors and 55 non-survivors. The data was recorded in different centers in Switzerland and under different protocols. We have 79 patients treated with hypothermia and 55 patients treated with normothermia. Each patient was exposed multiple times to auditory stimulations. We feed each of these trials through the network, giving us an output between 0 and 1, indicating if the trial was more likely to belong to a survivor, 1, or a non-survivor, 0. We then take per patient all of the trials, run them through the network, and then take the mean of the output to get 1 label per patient, indicating if they were more likely to survive or not. The network architecture that we used is called EEGNet and was designed specifically for decoding EEG signals. We did train the networks in a 10-fold cross-validation. However, in this presentation, I will only mention results of the best fold. In this illustration, we see one circle per patient showing their mean output of the network between 0 and 1 for survivors on the left side and non-survivors in orange on the right side. We also differentiate the train and test validation sets. You can see that we reach quite high AUC score on the test set of 0.83. We also reach a high positive predictive value of 0.92, meaning that if a patient had a network output above 0.5, this would indicate that they were more likely to survive. However, if that value was below 0.5, we cannot make such a strong claim. Next, we looked at the patients in the gray zone of our dataset. This subcohort contained 48 patients, so roughly a third of the patients. We can see that we reach a predictive value of 0.836, which is a little lower than the value for the full cohort, but still quite high. We have seen so far that we reach quite a high performance of the network in predicting outcome of coma. However, we also wanted to explore what features the network would learn. A recent study in our group looked at the phase locking value in hypothermia patients. The phase locking value looks at the phase locking and therefore synchronization of two electrodes. It is related to neural synchrony. If patients reach a high PLV value, the study showed a high positive predictive value for good outcome of 0.87. We did reproduce these results in patients treated with normal thermia. However, the positive predictive value is slightly lower for these patients, but the threshold was selected based on patients treated with hypothermia. Next, we looked at the correlation between the network's output and the PLV. We found quite a high correlation, indicating that the network seems to pick up some of the features similar to the PLV. So if we have a patient with a high network output, they will also have a high PLV, which are mostly survivors. In this case here, we also depict some exemplar EEG traces for survivors and non-survivors, both correctly and incorrectly predicted ones. The same study I mentioned before also looked at the Lempel-Ziv complexity, which is related to neural complexity. This study did not find any indication of outcome prediction for the Lempel-Ziv complexity. We did reproduce the overall distribution of LZ values for survivors and non-survivors in normal thermia, but we did not find any indication of a relation to outcome either. However, if we calculate the correlation of the network's output with the Lempel-Ziv complexity, we find quite a high correlation, meaning that also here the network picks up some of the features related to the LZ complexity. For patients with a high network confidence, we can see a low Lempel-Ziv complexity. And for patients with a low network confidence, we have quite a high neural complexity. So we have shown two examples of electrophysiological measures that seem to be related to the network's output and therefore features picked up by the network in one way or another. In conclusion, we have shown a high predictive power of convolutional neural networks for predicting ERP data, for auditory ERP data, a generalization across cohorts treated with different temperatures, and high predictive power for a subgroup of patients in an uncertain state. The network confidence correlates with the phase locking value and the Lempel-Ziv complexity, giving us some insight into what the network learned. Finally, the presented pipeline could be used in the future in a clinical routine as a positive predictor. And with that, I'm at the end of my presentation, and I would like to thank the members of our group as well as the funding resources. Thank you for your attention.